Good evening, ladies and gentlemen. I'm Peter Goddard, Director of the Institute for Advanced Study, and it's my pleasure to welcome you here this afternoon to this Institute lecture. Today, our speaker is Edward Witten, who is Charles Simonyi Professor in the School of Natural Sciences here at the Institute. Edward is a theoretical physicist whose work has played the leading role in redefining the scope of mathematical physics over the last 3 decades or so. Over that period, he has greatly influenced the development of the theories used to describe fundamental physics, including string theory and quantum field theory. Further, his work has also had a profound influence on research in a number of areas in pure mathematics, achievements recognized in 1990 by the award of a Fields Medal, the most prestigious award in mathematics, and he's the only physicist to receive this prize. Edward obtained his bachelor's degree from Brandeis University in 1971, majoring in history, and his PhD from Princeton in 1976. He then spent 4 years at Harvard before returning to Princeton University as a professor of physics in 1980. In 1987, he joined the faculty of our School of Natural Sciences as a professor, and he was named the Charles Simonyi Professor in 1997. His work has been recognized by a MacArthur Fellowship in 1982, the National Medal of Science in 2003, the Crawford Prize in 2008, the Isaac Newton Medal in 2010, and very, very many other honors. And as you see, tonight his title is Knots and Quantum Theory.
Well, thanks so much for the invitation and for the kind introduction. So, first of all, a knot is more or less what you think it is. It's a possibly tangled loop of string in ordinary space. For example, there's a picture of a knot. The main difference from knots in everyday life is that usually in everyday life, if there's a rope or a string, it's doing some job, connecting something or tying something. And you might run into a tangle, usually as a result of making a mistake. But there's something more than the tangle, namely the knot is connected to something. A knot, as understood by mathematicians usually think of the knot as freely floating in empty space. So in effect, they study the tangle for its own sake, abstracted from whatever a knot, a rope, or a string might do in the real world. Now, the example hopefully reminds us of something that we all know all too well in everyday life, which is that a knot can be extremely complicated. It can be very hard to make sense of a knot, to tell whether it can be untangled, and how to untangle it if it in fact can be untangled. And it can be equally hard to know if 2 tangles are equivalent. Now, questions like these may not sound like math if one thinks that math is just adding, subtracting, multiplying, and dividing. But actually, in the 20th century, mathematicians developed a rather deep theory of knots, with surprising ways to answer questions like the everyday question of whether and how, well, whether at least, a given tangle can be untangled. But before we go on, I'd like to address the following question, which is why I am interested as a physicist. So, even though knots are things that can exist in 3-dimensional space, personally, I'm only interested in them because of something rather surprising that was discovered in the last 3 decades. Much of the theory of knots is best understood in the framework of contemporary developments in quantum physics. So, in other words, personally, what I care about are not the knots, but the connections between the knots and quantum physics. The first knot polynomial was discovered way back in 1923 by James Alexander, who actually was a Princeton native and later not much later than the discovery of the Alexander polynomial. He became one of the first professors at the IAS. But we're going to jump ahead, and the story as I'll tell it begins in 1983 with the Jones polynomial, which was discovered by Vaughan Jones. And the discovery was made very close to the time when he'd been spending a couple of years at Princeton University. In fact, my wife and I met that family in connection with childcare long before we knew about the Jones polynomial. So Jones discovered a new property of knots known as the Jones polynomial, and his discovery led to a flood of new discoveries that's continuing to this very day. The Jones polynomial, in many ways, is very unusual. It's very modern and near the frontier of contemporary mathematics. And if you want to understand it fully, there's a vast theory. But at the same time, it can be defined in such an elementary fashion that one could teach about it in high school without compromising very much. There are not many developments in the frontiers of contemporary mathematics where one would say that. For example, I would think that nobody would try to explain Andrew Wall's proof of Fermat's theorem in high school. What Jones discovered was a way to calculate a number for every knot. So we'll call our knot k, and we'll write j sub k for the number that Jones calculates for the knot. There's a definite rule to calculate jk for any knot. It's a surprising rule that it works, but it's a definite rule. No matter how messy the knot is, you can calculate jk if you're patient enough. If jk is not equal to 1, then the knot can never be untangled. So once again, I've drawn a knot, the same one we had at the beginning. And if you think about trying to untangle it, first of all, you'll find if you look carefully that you can make a minor simplification. But I think you'll convince yourself after a while that you can't actually untangle that knot. But how would one prove that it's impossible? That's the question where Jones made a major advance. His answer is, calculate j sub k, and if it isn't 1, then the knot k can't be untied. So finding his method was very clever, but once it was discovered, anyone can use it. You just follow the instructions and calculate jk. The cleverness all goes into finding the instructions for calculating jk while implementing them. If you're patient, you can do, and you'll get an answer after a certain amount of work. Okay. People who study computational complexity will object that I'm underestimating the amount of work involved, but for now that'll do. How do we calculate jk? Well, one important rule is that it's 1 for the unknot. The unknot is simply a loop that isn't tangled. For all the other knots, we're going to play a little game. To start the game, we pick 3 favorite numbers, for example, 2, 3, and 5. They don't have to be prime numbers, although the numbers I picked for today are prime. And now we're going to do something that might seem to make life more complicated. Instead of a single knot k, we're going to consider 3 knots, k, k prime, and k double prime. If the knots we picked are related in a certain way, then we're going to declare that jk, jk prime, and jk double prime, the Jones numbers for these 3 knots, obey an algebraic identity that 2 times 1 plus 3 times the second plus 5 times the third is 0. The identity is so powerful that it enables one to calculate the j's. Now, how do we pick the 3 knots that participate in this identity? What I've drawn here is not a knot because there's a missing piece inside the blue dotted line. The question mark symbolizes the fact that there are 4 strands that end on the dotted line, and to complete a knot, you need to do something inside the dotted line to connect these 4 strands. So here, I've drawn 3 of the simplest ways that you might complete the picture by gluing something inside the blue dotted line. So if you take one of these 3 pictures and glue it in to replace the question mark here, you'll get 3 different knots, k, k prime, and k double prime. And then we declare that the functions of Jones, jk, jk prime, and jk double prime, should obey our identity. It's not very hard to see that this rule completely determines jk for every k. But I think I'll leave that for the question period. But that's the, I won't do it in front of you, but it would take a few more pictures, but it would be a simple argument. Now, given our rule, the hard part is not to calculate jk, but to show that there's never a contradiction. There might be a contradiction because there are many ways to apply the rule. You see, here's our complicated knot again. And I could have drawn the blue dotted line around any crossing in the knot diagram, any crossing in the picture. And then I could replace what's inside that little circle by the two other possibilities. And then this knot would participate in our equation together with two other knots. So there are many, many ways to proceed. As one could apply the rule to any one of these crossings, and moreover, we could have looked at the knot from any other angle in space, drawn a different picture representing the same knot viewed from a different angle, and we would have had many other ways to proceed. So our one equation really represents many, many different equations. And if you think about that a little bit more, you'll find that you easily have enough information to determine jk, but it's not that obvious that you will always get the same answer no matter how you proceed. The surprising part of it is primarily that we get the same answer no matter how we proceed. But what was shown by Jones and then in other ways by other mathematicians in the 80s who worked on this subject is that there's never a contradiction. You always get the same answer for jk no matter how you calculate it. The proof showed that Jones's recipe is correct, but it left the why question. Unfortunately, for those, if one doesn't work in mathematics or in some field like theoretical physics that uses a lot of mathematics, it can be difficult to understand the difference between learning what's true and learning why. But even though this difference is subtle, it's very important. The beauty of the why answers is a lot of the reason that people do mathematics. In the case of the Jones polynomial, what happened as people worked on the Jones polynomial, they discovered more and more remarkable formulas with less and less clarity about what they meant. But there was a clue. In fact, there were lots of clues. Going all the way back to Jones's original work, as the subject developed, it had many ties with mathematical physics. Bewilderingly many. If anything, there were too many links found between the Jones polynomial and mathematical physics. You could explain all kinds of things about the Jones polynomial in many different ways, and the answers often involve linking it up in one way or another with mathematical physics, but you built up a web of interesting connections and relationships and it was difficult to find a clear picture of what was behind it. Sometimes it's better to have one good clue than a dozen of doubtful merit. Personally, I was most influenced at that time by the people I've indicated here. IAS members Eric Verlinden, Nathan Seiberg, and Greg Moore, former IAS professor Michael Atiyah, and also the Japanese mathematicians Tsuchiya and Kaniya, whose work I think I learned about from Graham Siegel. It turned out that the explanation has to do with quantum theory. So I need to tell you a little about how quantum theory differs from pre-20th century physics. A classical particle that's traveling from one point to another gets there on a nice orbit that obeys Newton's laws. So it starts here and it ends here, and it travels on some nice orbit that, for example, might be an ellipse or something very close to an ellipse describing the motion of a planet. Now, a quantum particle instead can follow any path at all. A fairly typical path, by some ways of judging what's typical, might be quite irregular. So I've drawn one which is rather irregular by many standards, but not nearly as bad as a quantum path might be. A quantum path, the more closely you look at a quantum path, the worse it might look. So quantum paths by some measurements, a typical quantum path could be very, very complicated. Now, although the classical particle had a definite orbit, obeying Newton's laws, by which it got from the starting point to the final destination, the quantum particle can really travel in all possible paths. And here, for a particle starting here and ending here, I've drawn 3 possible paths. So I drew 3 paths that didn't intersect each other just to make it easier to fit the 3 paths on one picture. But in general, we had any 3 paths that started here and ended here, and I only drew 3 to give illustrations. Literally, in quantum theory, we allow all possible paths. Now, one important point is that we're not just quantum physicists, but we're also relativistic physicists, because relativity was invented in the 20th century along with quantum mechanics. So when I draw a path, you should really best understand it as a path in space-time, not a path in space. So the physical dimension of the real world we live in, from this point of view, is 4. There are 3 space and 1 time dimensions. But to understand knot theory, at least for the moment, we're going to imagine living in a world of only 3 space-time dimensions, 2 space dimensions and 1 dimension of time. But the discussion is relativistic, so we will not really distinguish space and time. We'll just be living in a 3-dimensional space-time. In a world of 3 space-time dimensions, the particle path might be knotted, and 2 of my 3 examples were knotted. Well, so we considered 3 paths that went from here to here. This one was wiggly but not knotted, but I've embellished the other 2 paths with a little knot that actually, well, first of all, it's a fairly familiar knot that we often run into by mistake in a shoelace, for example. Mathematicians know it as the trifoil knot. A quantum physicist has to sum over all possible paths by which a particle might reach its destination. How to do this sum is what physicists learned in developing quantum theory and ultimately in constructing what's now the standard model of particle physics. And if you major in physics and then go on to be a graduate student, a decent fraction of what you learn is how to do this kind of quantum mechanical sum. As I've stressed, quantum mechanically every path is possible. But it's not quite true that every path is on the same footing. Although any path is possible, if the particle traveled on a particular path, which I'll call k, and not coincidentally, I'm using the same letter k that we had earlier for our knots, then there's what's called a probability amplitude for the particle to arrive at its destination. And this amplitude depends on k. The way the amplitude depends on k is crucial for bringing order to a quantum universe. So all paths are possible, but in a certain sense, peculiar paths with a lot of zigzag are not very likely. By the time you've finished doing your quantum mechanical sum, you end up learning, because of the way the amplitude depends on k, that the very, very strange paths end up not making such an important contribution. So it's crucial to understand the probability amplitude that depends on k. Now, the quantum mechanical amplitude that the particle did travel on a path k is given by something called the Wilson operator, W sub k. For today, we don't really need to know how it's defined. All we need to know is that it's a basic ingredient in quantum physics, and for instance, physicists use it in calculating the force between quarks. So quarks are trapped in an atomic nucleus. If you want to know how that happened, you have to study the Wilson operator, W sub k. The connection between the Jones polynomial and quantum physics turns out to be simply that if we regard a knot as the spacetime orbit of a charged particle, then the Jones polynomial is the average value of the Wilson operator. So the quantum formula for the Jones polynomial is just that J sub k is the average value of W sub k, where this symbol refers to a process of quantum averaging. This formula is the Jones polynomial expressed in terms of quantum physics. Except that you need to know what kind of quantum physics you're planning to do. So the quantum physics that you have to do is a close cousin of what physicists usually do in gauge theory using elementary particles, but there's one very important twist. You have to do a slightly different version of quantum theory with a different action function, to use the technical phrase. So the version of quantum theory that you actually want is constructed using something called the Chern-Simons function for gauge fields, where the name refers to S.S. Chern, who was one of the founders of much of 20th century differential geometry, and our own James Simons, our friend and trustee, in whose honor we just dedicated the dining hall just half an hour ago. Now, so why am I telling you these things today? So it's not only because of wanting to relive my early days at the Institute, although that's certainly fun. This story actually has a more contemporary twist, which I've been working on for most of the last 2 years, and I want to tell you at least a few words about it. In everyday life, as we stressed at the beginning, a knot is a physical object that exists in space. But to interpret the Jones polynomial in terms of quantum theory, we've instead had to view a knot as a path in a space-time of only 3 dimensions. This is perhaps a less obvious viewpoint about what a knot means. However, around 1990, when he was a member at the IAS, Igor Frankl began developing pieces of what he hoped would be a new mathematical theory in which the knot would indeed be a physical object rather than a path in spacetime. The new theory was supposed to involve a more powerful version of the Jones polynomial. I wish I could say I gave him some good advice, but all I did was to say it wouldn't work because the Chern-Simons function does not have the right sort of generalization to 4 dimensions. It actually was a very good argument, and I'm still surprised it turned out to be wrong. Anyway, Frankl didn't listen. He kept developing the ideas with, Lou Crane and Michael Kovanov, who have both been IAS members at different times, among others. And finally, around the year, Kovanov was also a Frankl student, I guess, during this period. Finally, around the year 2000, Kovanov created what we now know as Kovanov homology, a refinement of the Jones polynomial in which indeed the knot is a physical object rather than the path of a point particle. So Kovanov homology is like the Jones polynomial in that once it was invented, it can be computed by an explicit set of rules. You don't need quantum physics to define and calculate Kovanov homology, just like you didn't for the Jones polynomial, although you may need quantum physics to fully understand what it means. So although both Kovanov theory and the Jones polynomial are given by an explicit set of rules, in the case of Kovanov homology, the rules are far more sophisticated than for the Jones polynomial. With Kovanov theory, we're leaving the world of things that we might consider explaining to high school students. For that, I think we'll limit ourselves to the Jones polynomial. Kovanov homology has had a lot of impact mathematically. For example, it was one of the main foci of a special program here in the School of Math a few years ago. In 2004, Gukov, Schwartz, and Vafa proposed a quantum interpretation of Kovanov homology using earlier work of Vafa with Hiroshi Uguri. So their story used plenty of avant-garde ideas about quantum fields and strings and all that. And it showed that Kovanov theory had a physics-based interpretation, but one that was surprisingly far removed from the story about the Jones polynomial. So their story was very beautiful and powerful, but I was always a little unhappy that it had so little evident connection with the quantum story concerning the Jones polynomial, and that made me think there might be a more direct route. And I spent most of the last 2 years trying to construct one. So the 2-year period actually began with a conference on Chern-Simons theory at Bonn, but I'll only get back to that at the very end. That conference was in the summer of 2009. So anyway, in a sense, I succeeded at re-expressing Kovanov theory in the context of quantum theory in a way that made the relation to the older story more transparent. But although I succeeded after all this work, it's a little hard to say whether I found a more direct route from quantum physics to Kovanov homology or just a somewhat different one. The main difference between Kovanov homology and the Jones polynomial is that the goal is more abstract. What the Jones polynomial associates to a knot k is a number jk, and I essentially told you how to calculate that number. But what Kovanov theory associates to a knot is a space of quantum states that we'll call hk. So if you think of the knot as a physical object in three-dimensional space, then hk is the space of its possible quantum states. For instance, an example of a knot-like object, which quantum physicists study, would be a vortex line in a superconductor. So a question you could ask that's not totally silly is whether hk might be the space of quantum states of a vortex line that is traversing the knot k. The answer is no for vortex lines in conventional superconductors, but condensed matter physicists keep discovering funny things, and it's at the fringe of what you could imagine that eventually a real quantum system would be discovered for which the space of quantum states would be the Kovanov homology of that knot. But even if that doesn't happen in the real world, Kovanov homology, you could imagine being similar to that. Because the theory is now in 4 space-time dimensions instead of 3, the knot is a physical object in 3 dimensions, and there's still time, it involves ideas and methods that are even closer to real particle physics than those that go into understanding the Jones polynomial. One important idea is symmetry between electric and magnetic fields. This is called electric-magnetic duality and was pioneered by Goddard, Neutz, and Olive, all of them former IAS members, in the mid-70s. Since the mid-90s, this has been one of the main ingredients in studies of quantum field theory and string theory. For instance, Seiberg and I used it in our work on supersymmetric gauge theory in the 90s. And it turns out to be one of the important ingredients in understanding Kovanov theory. So another ingredient of string theory also turns out to be important, which is extra dimensions. So even though what we want is supposed to be a theory in 4 space-time dimensions, it turns out that you can understand it better by relating it to theories in 5 and 6 dimensions. The biggest surprise of all is that even though it can be defined by an explicit recipe with no reference to quantum physics, and that's precisely how it was discovered, Kovanov homology can also be understood, perhaps much better, using the most modern tools of quantum field theory and string theory. Probably the full story involves physics ideas that we don't understand yet. So I won't tell you, in a moment I'll tell you a little bit more about the motivation that led to the work, but I won't tell you more about the details of what I did, except to say maybe one thing, which is that electric-magnetic duality was important, and among other things, it was important in overcoming the objection I had raised to Igor Frankl back in 1990. So to the extent I have a good excuse for having given what proved to be wrong advice, it has to do with the fact that even though the basic idea is much older, the use of electromagnetic duality wasn't well understood at the time. So really, to use electromagnetic duality along with other ingredients to understand Kovanov homology wouldn't have been possible back then. Many of the important ingredients just didn't exist 20 years ago. So we still have a bit of time, and what I want to tell you about now is about some of the other clues that were important in my work on Kovanov homology. So I've already mentioned one, which is that Gukov, Schwartz, and Waffe had already found an answer of sorts, linking Kovanov homology with aspects of the string theory story. And, well, that was a very important clue. Starting from there, I reformulated it a little bit in a way that could make more transparent the connections with gauge theory and the Jones polynomial. But certainly that was a crucial starting point. But there was another clue that has to do with the Langlands program. The Langlands program is really part of number theory, and as such, I don't know much about it. So my guess is that physics will eventually have something to say about number theory, but probably not for a while. If I had to guess, not during my career. And in any case, whether that's true or not, certainly, personally, I don't know much about either number theory or the real Langlands program, which is an approach to number theory. But, okay. Just to orient you, however, for those of you who have never heard of it at all, I'll just say that it's an extremely wide-ranging program in and beyond number theory. The beyond we'll mention in a second. But the in number theory part, although I probably know more about this than most of you do, is that a very, very small special case of the Langlands program, which is a vast thing in its own right, was a crucial step in Andrew Well's approach to proving Fermat's last theorem. So perhaps that'll orient you just a little bit to the fact that the Langlands program is really a vast perspective. And it's got ramifications that go way beyond number theory. And in fact, there is a geometric version of the Langlands program, which was largely pioneered about 20 years ago by then IS members Vladimir Drinfeld and Sasha Bailenson, now at the University of Chicago. And it's fascinating that the Langlands program does have this geometric counterpart, but again, just to put it in perspective a little bit, I think it's the case that the work on the subject is mainly motivated by its interest in number theory, and that even for Drinfeld and Bailenson, the reason for creating the geometric analog was the hope of finding something simpler that would eventually shed light on the number theory. Now, for years I was puzzled about the geometric Langlands program because it made heavy use of familiar ingredients of mathematical physics that I know, and that my colleagues here at the Institute know, but they were scrambled in a totally unfamiliar looking way. It was roughly as if someone had randomly dumped the chess pieces on a chessboard. The pieces were familiar, but not the patterns. And perhaps you would learn in that case that the game that was being played was not chess, but some other game that can be played with the same pieces. And that's why the patterns didn't look familiar like patterns that would come from a game of chess. But in this case of the ingredients of mathematical physics, I really feel that as physicists we aim to know the important patterns by which those pieces can be assembled. And if there's another pattern or a seemingly different pattern, it either should be absorbed as part of the physics we know or should be better reformulated by expressing it in terms of the more standard patterns in which physicists develop this kind of mathematical physics. So the inability to do either of those two really nagged at me for a long time, definitely more than a decade. And eventually I spent a couple of years showing that the geometric Langlands program actually can be reformulated in a way that, well, I'm only going to give you a physicist's view, but the physicist's view is that in the long run it's more powerful, but in any case, in a way that looks more natural to physicists. So, okay, that's how I spent my time for a certain part of the last decade. My collaborators, I should mention, were IAS members, former IAS members, Kapustin and Gukov, the same Gukov who appeared in our story a little while ago for a different reason. And the ingredients were some of the same ones, such as electric-magnetic duality and higher dimensions, that I mentioned in telling you about Kovanov homology. So during the same period, I was also unhappy about Kovanov homology because it looked like another case where the chess pieces had been dumped at random on the chessboard. but I had no idea that it was in any way connected with geometric Langlands. When I was trying to make sense of Kovanov homology, I came across the work of mathematicians who had described Kovanov homology in terms of something that technically is called moduli spaces of Hecke modifications. Now, I won't try to tell you what those are, but I will tell you that they'd caused me a lot of frustration over the years. They're one of the main ingredients in geometric Langlands, and it was clear that you couldn't rearrange the pieces on the chessboard without understanding what they meant. So I'd spent years on and off daydreaming about what geometric Hecke modifications meant in physical terms. Well, eventually the answer appeared. They correspond to something that physicists use, the 't Hooft operators that are used in understanding how it is that quarks are trapped in atomic nuclei. 't Hooft is another former IAS member, and I think this work was done in the late 70s, a couple of years after he had been here. The answer, though, had crossed my mind suddenly while flying back from an event that Charles Simoni had hosted in Seattle. Charles had an event for the Institute, so Peter Goddard and I think Rachel Gray had flown out there, and I gave a little talk, which I was supposed to give without visual aids. That was a little bit of a challenge. And then on the way back, well, probably I would have been asleep if I could have slept, but I couldn't, so I ended up daydreaming about geometric Langlands, and on that particular day, it suddenly struck my mind that the Hecke modifications had to do with the 't Hooft operators. That was one of the two best ideas I've had in an airplane. Now, so anyway, by the time I ran into this work of Kaudas and Chemnitzer, who used these Hecke operators for Kovanov homology, it was easier to understand what to do. I knew how those fit into gauge theory, so basically I had to rearrange the ingredients I had already used for geometric Langlands. So there was one more ingredient I'll mention. So Chiara and I were on sabbatical at the CERN laboratory near Geneva in 2008 to 9, and they weren't discovering the Higgs particle and doing all kinds of other fun things because unfortunately that was the year of their accident. So all the great physics that is coming out of the CERN laboratory is just beginning to come out this year rather than the year we were on sabbatical. Anyway, at the end of the year, we attended a conference on Chern-Simons theory at the Hausdorff Institute in Bonn. And, well, I had another one of these experiences involving chess pieces that are misarranged. Here I was reminded for perhaps the umpteenth time of certain work by mathematicians as well as by my former student, Sergei Gukov, who I keep telling you about. And this work had always embarrassed me because it couldn't quite be understood in terms of the standard sum over quantum paths. So the Jones polynomial, if you set things up properly, the Jones polynomial is the average value of the Wilson operator. But some of the rules were being violated here, and since I take the rules of quantum theory seriously, I'm very unhappy with something that superficially uses those rules but in fact breaks them in an essential way. So I really wanted to understand, and this is something I'd wanted to understand before without success, but I went back to it after this meeting. I wanted to understand what you were supposed to do with the quantum sum over paths in order to get the sort of results that I was hearing about at this meeting. So I spent the fall of 2009 very, very slightly generalizing the usual sum over quantum paths so I could use it to understand what I'd been hearing about in Bonn. So I wasn't aiming to understand Kovanov homology. So, well, I wanted to do Kovanov homology, but I didn't know how to. But at the end of this, by the time I had made this very slight generalization of the usual sum over paths, I discovered that I'd actually arrived at a good starting point for Kovanov homology. So I think that's as much as I'll tell you about what were the clues, and as well as telling you the clues, I've tried to also give you a hint, a couple of hints, about the fact that in doing research, one spends most of one's time floundering around in the dark and actually stuck. Okay, so I'll stop there, and since I did end a few minutes ahead of plans, we do have ample time for questions, I think. So I think if you want to ask a question, there are microphones handy. I'm sure there must be a question or two. Yes? Oh, thank you. You're greatly appreciated for asking the first question.
Actually, it's two. One is that when you first showed us that equation,
Yes.
excuse me, and used the numbers 2, 3, and 5
Yes.
in the equation that equals 0.
Yes.
Do you have to use those 3 numbers, or can you substitute any 3 real numbers?
So the answer to that question is that you can use essentially any numbers with a very mild restriction. So the way Jones formulates it was to use 3 algebraic variables, a, b, and c. And then the Jones polynomial is not a number, but a rational function. But I wanted to keep it as simple as possible, so I picked 3 actual numbers for a, b, and c.
And the other question is, you talked about the sum of all those possible paths.
Yes.
But there's actually an infinite number of
Yes.
possible
Yes.
paths, aren't there?
Yes.
So the only way you can sum them is because of that probability, because some are more likely than others?
Yes. So first of all, what I call the sum is really an integral, technically. So you use
Okay.
calculus, albeit calculus in infinite variables. So nevertheless, going back to Feynman, physicists traditionally call it a sum over paths. And I couldn't see any reason not to follow the traditional terminology here because I thought it would make it easier for everyone to understand. And it is the usual technical terminology anyway. It's just like when you get to a very, very advanced level, number theorists start referring to what they do as arithmetic. So first you study arithmetic, and then the math gets more advanced, and then your reward for getting to a very, very high postgraduate level is to call it arithmetic again. So similarly, the quantum sum over paths is traditionally called a sum, even though it's not just an integral, but it's an integral in infinite many variables. You're completely correct, though, that having this non-trivial amplitude in the sum over paths is totally necessary for that sum to make any sense at all. Yes?
There is this famous paper of Eugene Wigner on the unreasonable effectiveness of mathematics in the natural sciences. It seems like you are suggesting that one should write now another on the unreasonable effectiveness of physics in mathematics. How wide, how broad is this impact? Can you tell other examples?
I don't know, but it wouldn't have survived people 200 years ago or 300 years ago who certainly knew that calculus had come out of studying the motion of the planets. A general comment I'll make, though, is that physicists don't understand string theory very well. And I believe that's one of the main reasons for being able to come up with mathematical surprises. If it were well understood, then it would also be possible to explain it to mathematicians, and then if there was math coming out of it, the people doing that work would probably mostly be mathematicians. But since it's not well understood, it's very hard to explain what it is to mathematicians. And since it apparently contains deep mathematical secrets, they keep coming out bits and pieces at a time. So the I don't know answer to your original question of how broad this is. Of course, I'm giving you an I don't know for the 21st century, not for the 18th century. But the main reason for the I don't know is not knowing what the answer is to what string theory really means, and therefore not having any idea how broad the ramifications would be. Yes? Well, okay.
I only have
we'll
one
get to you in
question.
a second.
Yes?
Okay. Go ahead.
Do you have students along this path?
Yes, I've had students, certainly. I told you several times about my former student, Gukov. Another former student I mentioned in the talk was Vafa.
I mean now, graduate students.
Well, that's a slightly tricky question. Maybe we should discuss it later. I'm not sure what the answer is because one who was doing very well has sort of disappeared temporarily.
You made the intriguing remark in passing that you thought quantum physics was going to be useful for number theory eventually, but not just yet. Can you perhaps elaborate on that? Can you say what sort of number theoretic questions it might be useful for, and why it's not useful at the present time?
Well, it's easier to answer the second half. Physics is not, well, there may be some limited questions in number theory where presently known physics-based methods are useful, and probably that has happened sometimes. One could point to examples if I wanted to. I could, but they would be too specialized. But I had in mind something a little bit more ambitious, like whether physics could affect number theory in a really serious structural level, like shedding light on the Langlands program. I'm only going to give you a physicist's answer, but personally I think it's unlikely that there's an accident, that geometric Langlands has a natural description in terms of quantum physics. And I'm confident that that description is natural, even though I think it might take a long time for the math world to properly understand it. So I think there's a very large gap between these fields of math and physics. I think, if anything, the gap is larger than most people appreciate. And therefore, I think that the pieces we actually see are only fragments of what must be a much bigger totality.
You talked earlier about the beauty of mathematics. And as a mathematician, I resonate with that a lot. How do you talk about the beauty of physics, and where do you find the connections?
Well, first of all, I apologize slightly for having stepped in as a pinch hitter today to talk about the beauty of mathematics. It would have been more natural for me to talk about the beauty of physics, but given the nature of today's lecture, I did have to. The remarks I made were kind of necessary for today. So I can assure you that the physical theories are extremely subtle and elegant.
Hi, excuse me. So
Well, we should have some questions on the right side. Is there a...
oh, thank you.
why don't you...
Okay. In mathematics, there are undecidable questions. Do you think there are undecidable questions in physics?
The question is if there are undecidable questions in physics. I hope not, but sorry. It's a funny question because you have to decide what you mean by a physics question. So if you start asking questions about how assemblies of infinitely many particles would behave, not worrying about the fact that you can't realize it in the real world, there almost certainly would end up being undecidable questions. So you'd really have to decide what you meant by physics and what class of questions you're interested in before you're... But I think what you're asking is, although it's still slightly imprecise, are there things you'd really want to understand about physics that would be undecidable? My answer is going to be, I hope not. But to many of these questions, I'm only going to give a physicist's answer.
I have a question. So recently I heard there was a lecture by Susskind, and he said there is a relationship between eternal inflation and periodic number theory. Is this kind of relationship between number theory and quantum and physical theory you respect it? Thank you.
So the analogy they made between eternal inflation and periodic numbers was interesting, but it's not yet deep, certainly. It's conceivable, it's a clue about something much deeper, but that's a long way off.
Well, Edward, thank you very much for a very fascinating talk.
No problem.